right, this is for part E. We want to find the error bound, find an error bound for the approximation from the part C. So we did the part C earlier, and in part C we have the approximation, right? We have the error right here. This is the approximation, right? When you have the approximation, it always gets, you have some error. Now let's apply this theorem to find the error bound for part C. Now, because we have 3 nodes in this problem, x0, x1, x2, n is 2. And in this theorem, in other words, you have to find the third derivative because n is 2, right? So n plus 1 is 3. You need to find the third derivative of the function. So let's find that here. So we first find the derivative. F prime, by the way, f is 1 over x. So f prime of x is equal to negative 1 over x squared, because f of x is 1 over x. Now just continue to find the other derivatives. So f double prime of x, you may pause the video now so that you just do a little exercise. Find all the derivative until the third derivative. Alright, hopefully you get the same answer as mine. I have all these derivatives written down here now. So these are all the derivatives. Let's apply this formula. Let's apply the theorem. So in this case, our error, the error is equal to, so here this will be f third derivative of xi, right? Because n is 2, divided by 3 factorial. And here this is x minus x0, which is 2. And then x minus x1, which is 2.75. And then x minus x3, x2, which is 4, the third node. So in the third derivative, this guy, we need to plug in xi. So the third derivative is negative 6 over here the x to the 4th, because we need to plug in xi. So it will be xi to the 4th. Be careful here. Divided by 6 factorial. Now, remember what we are looking for? We look for the error bound for the approximation from part C. In part C, we use P2 of 3. We use P2 to find f of 3, right? So x is equal to 3 in this case. Now, therefore, here I will use 3 minus 2. 3 minus 2.75. And 3 minus 4, because x is 3 in part C. At the end, again, whenever you look at error, you really don't care about the sign, so you want to use absolute value right here, okay? Absolute value. And here this xi is in between 2 to 4, somewhere in between these 2 to 4. Your job, you see all these are constants now, except the xi. So your job is to look for a xi so that this quantity is maximized, right? So that's the error bound. Now, obviously, this xi, if you look at this function, the xi is in the denominator. How do you maximize this this quantity? You choose the smallest value you can get for xi, and then it will be maximized. So with that, we continue to have. So ignore all the negative sign and simplify all the values. So it will be 1 over let me do a little cancellation. That might be easier. So this 6 is cancelled out with this. I'm sorry, this is not 6 factorial. It's just 6. So cancel out with this 6. So we are left with 1 over xi to the power 4. And this is going to be 1. This is 0.25. This is 1. I simply ignore all the negative sign. And then, like I said, to maximize this value, you pick the smallest xi value, right? So I'm going to pick 2 for xi times 0.25. So therefore, we have 0.015625. So this is the error bound. Let's do a quick comparison, if you can recall. So let's, okay, right here, I have the screen showing both. The first one is my absolute, the true error, 0.00378. On the bottom, right here, is the error bound. Okay, so you should not be surprised the true error is always less than the error bound. That's why we call that as error bound, right? So this is part C. Now, I do want you to look at the another problem. This problem is find error bound for the Lagrange interpolating polynomial found on part B when the polynomial is used to approximate f of x for any value in this interval. So in part E, you're looking for the error bound for this particular approximation, right? Here we are going to say, hey, now this time x is not fixed. X can be any value in between 2 to 4. Let's find the error bound for this particular one. So in this case, again, we need to use the error formula, but x is not known, x is unknown. So our error will be f xi, third derivative of xi, which is the same. So 6 negative 6 over xi to the power 4 divided by 6, which is 3 factorial. Here, this x is not 3 anymore, it's just x. And x can be any value from 2 to 4. So x minus 2.75 and x minus 4. All right? Where x is in between 2 to 4, and also the xi is between 2 to 4. A little simplification. First of all, this 6 and 6 can cancel. So, and then I ignore the negative sign, so I have 1 over xi to the 4th, x minus 2, x minus 2.75, and x minus 4. I would discuss this separately. For the xi, it's clear that, excuse me, for the xi part, it's clear that to maximize this guy, I have to pick the smallest xi value you can get, right? So the xi is clear, just pick 2. Now we need to find x value to maximize the products of these three terms. This is all about calculus. You find critical value and then you find its maximum value. So I'm gonna continue from here. Like I said, what we need to do is to find the maximum value of this last quantity here, and then find an x value so that this is maximized, right? So I cheated a little bit here. I type in the function into Mathematica. I just call this as my g function g. I want to look for the x value so that this is maximized, where x is from 2 to 4. So in Mathematica, I can use expand to get this to get the polynomial. Or you can just multiply out. Okay, so this is going to be 1 over 16, and again, this is I just copy that here. It will be, let's just copy that down here. And now the next step is to find the derivative of this guy and set that to 0, right? To look for critical points. Again, this is very easy to do it by hand because those are just polynomial. I'm gonna just quickly take advantage of Mathematica. I just find the derivative, and I should expand the derivative and set that to 0. So expand the derivative, set that to 0. So this is my the next one. So to the next step is to maximize this term. Okay, to maximize this term, I already call this as g of x. So I will find the g prime, which is this guy, and then set this to 0 to look for the critical point, and use quadratic formula. It's very easy to find that x is 7 over 3 and x is 7 over 2. So two values. And remember, this x is also from 2 to 4. This is a closed interval. To find the maximized g of x, the maximum value, we need to evaluate g of 2, g of 4, the boundary points, and g of 3, 7 over 3, g of 7 over 2, which are critical points. And it turns out that g of 2, so you just pick the largest of those, and that would be the maximum value of g. And again, I take advantage of Mathematica. I type in g of 2, g of 4, g of 7 over 3, g of 7 over 2. I ran it. Again, you look for the largest absolute value. So this guy actually is the largest. So 7 over 2 creates the largest g value. So with that, so this is the one that we should pick, right? So which is negative. Actually, in its fraction form, it's negative 9 over 16. I have that on my notes. Please verify that. So now we are gonna close this. Like we can now finish this problem. So we can see that, hey, this is less than or equal to. By the way, I think I should use less than or equal to right at this point, because I bound the 1 over xi to the fourth, right? So I should use the less than or equal to, and then I continue to use less than or equal to here, 1 over 16, which is 1 over to the fourth, and here I plug in 7 over 2, and this is what we are supposed to have, but we ignore the negative sign, so 9 over 16. Okay, so and which gives us the 9 over 256. So this is the error bound for the last problem, and for using the P2 we developed to approximate f of x for any x in 2 to 4. So this concludes this part.